Hello everybody and welcome to a new video. Thanks for sticking around after my scary little disclaimer there at the beginning. So we're playing around with mains voltage today. So what exactly are we doing? Well, we're going to have a look at this interesting, very old power supply. So on the outside of this power supply it claims that it produces 12 volts of DC. But how does it do that? We've got mains voltage coming in on this side of the transformer. We've got 3 taps on the other side of this transformer, and then 2 diodes, 3 caps, and a resistor. How does this produce DC? Well, it doesn't exactly, but it does a fair good job at it. So let's have a quick look at the circuit diagram, because I did reverse engineer it. So let's have a quick look. So we've got our mains voltage coming in on this side of the transformer. Now this is a 5-to-1 transformer, which means that for every 5 windings on this side, there is 1 winding on this side. And that means that it takes this 120 volts on this side and puts out 24 volts. 24 volts on this side of the transformer. But it's a center tapped transformer, which means that on this side of the windings we've got 12 volts, and on this side of the windings we've got another 12 volts. It just occurred to me that I probably should have made this a back to basics video, but whatever. Anyway, so if you watched last week's back to basics video, I think it'll be last week's, it might be the week before's. Anyway, the half-wave rectifier back to basics video, which I'll link right here. Oops, I'll link it right here. If you watched last week, or if you watched that back to basics video, you'll know that this here, if you just look at this section here, that's a half-wave rectifier. And this section here is another half-wave rectifier with a little capacitor across the diode. And I'm not entirely too sure what that's for, but I have a theory. Anyway, so the waveform over here is going to look like this, and the waveform over here is going to look like this. And that's very important, the distinction that this one is going in that direction and this one is going in that direction. Because on this side is being half-wave rectified, so we're getting that half-wave rectified AC signal out like this. And then on this side, we're getting another half-wave rectified signal that looks, where should I put it? I'll put it here. That looks like this. So when you tap off of the center here, what you're getting is a full-wave rectified signal that looks like this. And then that runs through this filter cap here. I have no idea why this is here. This 4.1 meg resistor, I do not know why they're grounding this off through the filter cap to the neutral line. That's very weird to me. But anyway, because typically you want these to be isolated from the mains voltage, and if you have this resistor here, it's no longer isolated. There's not that galvanic isolation with the transformer. So if anybody knows why they would throw this 4.1 meg resistor here, basically removing the isolation, let me know in the comments. Anyway, so your load voltage is tapped off of these 2 points here across that capacitor. Positive here and negative here. So that's what it looks like. Now, I thought it might be fun to probe around this thing with an oscilloscope and a voltmeter, just to see what it looks like electronically. So we're going to go ahead, and I've got my power strip here turned off just for safety, and then we're going to plug that in. Now we're going to turn it on. This has now become dangerous. Do not do this at home unless you are a trained electrician. Now, we're going to go ahead and turn on my multimeter here, and we're going to do something that I haven't done with this meter in a very, very long time. We're going to change the mode to AC. So, we know that this is the negative side, so if we take this and we measure it here, we get 11 volts AC. And if we measure it here, we've got, apparently, oops, I'm not even getting a reading. There we go. We get another 11.5 volts AC. Now, if we measure across here, you'll notice it wiggles around a lot. And the reason why it's doing that is because, because of that capacitor. But if we were to average that out, it would look like 24 volts. Now, if I change this mode to DC, if we measure across this again, we'll notice that it's actually at about 16.11 volts without all that capacitor noise. So, let's experiment a little bit with the oscilloscope. Alright, where's my oscilloscope probe? There we go. Alright, so if we plug in here, we should get a nice, come on, clip in, there we go. We should get a nice sinusoidal waveform. And you'll notice the waveform starts here and then it goes down and then it goes up, right? Now, if I understand correctly from the construction here, if we go over to this side, I'll just clip onto this. Oh, it's going in the same direction. That's interesting. Oh, you know why it's doing that? My oscilloscope is... If I had two channels, I'd be able to show you how the waveforms are actually 180 degrees out of phase. And if I go over to this side, we'll just get a flat waveform that's at about, well, let's see what the computer has to say. Our probe is still set to times 10, so let's go ahead and set it to times 1. And we'll set the volts per division to 5 volts per division. So 5, 10, about, well, yeah, I was about to say about 16 volts, and it says 16 volts right there because I'm not paying attention. But that's just the DC waveform. Now if we go ahead and switch to AC coupling, I wonder what happens if we do that. It falls down to just a flat waveform because of the filter cap cleaning out any AC noise. So I think the next experiment I'd like to do, I'm actually mainly doing this so I can learn. Let's see, I wanted to see if I could pull the half-wave rectified signal. Let's see if we can, we're coupled AC again. No, we don't get a, yeah, we just get a DC signal there. I wonder why. It's probably because of that capacitor. Okay. I want to see if I can actually just probe out the half-wave rectified signals out of this circuit. So we're going to go ahead and what is it called? Muntzing, when you just cut out random components until it stops working? Alright, so let's remove the capacitor from the equation here. Alright, the capacitor is now removed. It's a big honkin' capacitor, and I should probably ground it just to be safe. Oh, I see that. Oh, you probably... Yeah, there we go. You see those sparks? That's the 1000 microfarad capacitor grounding out there. There we go. So that's now discharged. If I had touched that, I probably would have gotten a nasty little zing. And that's why you always ground a capacitor before touching any of the leads. Alright, let's turn this back on and have a look at the waveform now with no filter capacitor. Interesting. If we couple over to DC... Ah, there we go. Okay. So there's our full wave rectified signal there. There we go. We'll just set that to that. And if we go over to here and pull that graph back up, we'll see that the voltage peak to peak is 12.08 volts with an average of 11.27 volts. So that looks good there at 120 hertz. Now that's interesting because we've got a 60 hertz signal coming in, right? Well, it's 120 hertz because we've taken two of those signals and overlaid them on top of each other. So that's nice to see. But still only seeing one. I would have liked to have probed out only one of the rectified signals, but I guess I would have to there we go. I guess I would have to cut one of the diodes out in order to get just half of the rectified signal. Now, I'm wondering if this waveform is going to change much if we remove these two capacitors, which I think provide a little bit of smoothing to the half-wave rectified signal. So let's go ahead and remove those from the equation. Now I've turned this off in case any of you are wincing thinking that I'm touching a live circuit. Alright, so that 1 nanofarad capacitor is now gone, and I want to... Well, let's actually probe it now with one of the two little filter capacitors removed. Oops. Aha! That's interesting. So before we just had the waveforms kind of stopping here. Now we've got a sharp peak downwards, which would be indicating the side of the circuit where we removed the filter cap. So if we remove that other filter cap, we should have these sharp peaks down on both sides. Let's see what happens. This is actually kind of fun. I've never done anything like this before. How are we doing for time? I've got 5 minutes. All right. So let's go ahead and probe the signal now. And there we go. We've got a full wave rectified signal there. These little caps were keeping those peaks from going down a bunch, and then this this big cap here was keeping the peaks completely flat. Now, just for fun, let's reintroduce. Actually, you know, before I do this, I'm just going to go ahead and there'll be a blip. All right, and we're back. I just wanted to restart the camera so that I'd be able to continue experimenting here without fear of the camera running out of recording time. So let's go ahead and reintroduce this capacitor like that. Turn that back on. Alright, get the negative of the probe there and the positive of the probe there. Let's see what we got there. Yeah, so, I mean, even without these little filter caps, the waveform coming out there is extremely smooth. And that's because this cap is just so way enormous. It fills up with energy and it keeps any sort of sag from the peaks, which we'll talk more about those in the full wave rectifier back to basics video, which if I've already done it, there'll be a card right here. If I haven't done already, it'll be next week. Anyway, so that's interesting. Let's continue Muntzing. I really hope that's the right term. Alright, and we'll take that off and watch. Oh, and didn't do it that time. Oh well. Make sure that cap is grounded out. The next thing I want to do is I want to Muntz out this resistor and see what that does to the waveforms, if anything. Alright. So we've now restored the galvanic isolation of the circuit. Let's pull that out. It's a big, it's probably 3rd watt resistor there. Yellow, oh, that's yellow-violet green. So that's 4.7 meg, not 4.1. I thought that was brown, but I guess it would have looked brown through this yellowed, whatever this is. So 4.7 meg resistor there. Power it back on. Now this is now galvanically isolated from the mains, which means I could get away with touching those without fear of lighting myself up at mains voltage. But I'm not going to. So let's go ahead and have a look there. Oh. Interesting. So it seems like this style of power supply actually needs... Oh. Let's turn the power supply back on. Did I remove that resistor with the power supply live? That was stupid. Alright, so... That's interesting. Let's pull in the multimeter here. I'm learning as much as you folks are in this video, because I genuinely am not entirely too sure what I'm doing here. Alright, so that still says 11 volts. And that still says 11 volts. And right here... Wasn't that weird? Huh. Am I getting... Oh! That's right. It wouldn't show as an AC waveform. I needed to couple this DC. That's something I'm going to forget a lot. So we still have a full wave rectified signal coming out here. And it doesn't seem to be appreciably changed by the presence of this resistor. Let's reintroduce the resistor. Actually, let's turn that back on real quick. We'll freeze that waveform. Alright. So let's clip that resistor back on there. And then clip this resistor. How are we doing for time? This is going to be a longer video, apparently. We'll clip that resistor to that. Alright, now we'll power the circuit back up, and we'll unfreeze the waveform and see if there's any difference. No appreciable difference. So, yeah, I'm not too sure why that resistor would be there. except to purposefully defeat the galvanic isolation of the transformer. Interesting. Alright, so let's move all this stuff out of the way again. And we're going to do one last thing. And that is, we're going to clip one of the diodes off. And now, if we turn this waveform back on, we're going to see a very classic half-wave rectified signal there. And then if I were to go over here and clip onto this one, I didn't leave myself much lead left. Yep, okay. If we unfreeze it, we've still got the half-wave rectified signal. So that's an interesting video. I'm definitely going to sit on this until after I've done my full wave rectifier video, so I guess we'll see you guys next time. If you haven't already, consider clicking here to subscribe. Over here will be a video that YouTube thinks you'll find interesting based on your watching habits. Right here will be, I don't know, teardowns? Yeah, I guess this is a teardown. And right here on top of the oscilloscope will be my Patreon link, which you can use to support videos like this. Thanks for joining me. Bye-bye.